Hello mathematicians. Today we will see um, on another problem asked in the CSIR June 2014. It is part B problem, question number 27. So it is a very interesting problem from linear algebra, and we're going to use Rank-Nullity Theorem. Just Rank-Nullity Theorem means to solve this problem. So Rank-Nullity Theorem is one of very important concept in linear algebra. Using Rank-Nullity Theorem alone, we can solve many problems in CSIR. So you try to understand completely everything said in the video. If you have any doubts, please let me know in the comments. Okay, let's begin. So it is given that M cross n of R is the set of all m by n matrices with real entries. Okay. Then we are talking in all these options we are talking about M2 cross 5 of R. So basically we are looking at matrices of this form. So it has 2 rows and 5 columns. So it is a we are interested in 2 by 5 matrices only as far as this problem is concerned. Okay, all the options are about 2 by 5 matrices only. Okay, now what is a 2 by 5 matrix? What it represents? Any 2 by 5 matrix is actually represent a linear transformation from r power 5 to r square. Note that it is not a linear transformation from r2 to r power 5, but r power 5 to r square. Okay, so that is our first observation. Okay, now we have understood a 2 by 5 matrix as a linear transformation from r power 5 to r square. Next, in all the options, they are talking about the null space. Okay, so in every option, they are talking about very much about the null space. So let's recall what is null space. And so what is the null space of a matrix A? So now now linear transformation R power 5 is the domain, R2 is the codomain. So null space is nothing but set of all elements in the domain such that Ax equal to 0. So set of all elements killed by the matrix A. Or equivalently we can say this is the kernel of A. Therefore null space of A is nothing but kernel of the matrix A or kernel of the associated linear transformation. Now the elements of null space are collected from R power 5, the domain. Therefore, this kernel of A is a subset of R power 5. Okay, so kernel is a subset of the domain. Therefore, what we get, therefore the nullity of A. You see that the R power 5 has dimension 5 and this kernel is a subset of R power 5. Therefore, the dimension of the null space, that is what we call nullity of A. Since this null space is subspace of R power 5, the nullity of A is less than or equal to 5. Okay, that is our first observation. So for any linear transformation from R power 5 to R square, the dimension of its nullity will be always at most 5. Next, in the rank nullity theorem, the name itself says it's a rank and nullity theorem. So we have defined nullity. Next, we define what is a rank. To define rank of a matrix, we need the notion of range of A. So range of A is same as the range of a function. What is it? So you take it is the image of the so the matrix can be thought of as a linear transformation from r power 5 and r square. Then we just look at the image. You see this is this set is nothing but, so A is a function and you look at its image of the domain. So domain is r power 5. Okay, so you take an element, all possible elements from r power 5 and find all possible images. That is our range. Now we have applied x, we have applied a on x, right? Therefore it is a image. So image will be a subset of the codomain. What is codomain? It is R2. Okay, therefore range is always a subset of the codomain. Now in our case it is R2. Now the dimension of the I'm sorry, there is a mistake. The dimension of the range, dimension of the range space of A is what is defined to be rank of A. Okay, now the range of A is a subset of R2 and R2 is a dimension 2 space. Therefore, rank of the matrix is at most 2. So, what we have observed, if A is a linear transformation from R power 5 to R2, then the nullity is at most 5 and the rank is at most 2. That is our first observation. Now let's state what is Rank-Nullity Theorem. So if A is a linear transformation from R power n to R power m, it is a linear transformation. Then you take this n. This n is equal to nullity of A plus rank of A. Okay. Okay, so this is a very powerful theorem, one of the powerful theorem in linear algebra. We see how to use this theorem in proving the option. Okay, so let's first review the first option. So in first option, they are saying that there exists A belongs to there exists a 2 cross 5 order matrix, real matrix, such that its null space has dimension 2. Or equivalently, they are saying there is a 2 by 5 order, 2 cross 5 order real matrix whose nullity is 2. So we assume there is a matrix. So 2 by 5 matrix means it is a linear transformation from R power 5 to R2. We assume that suppose the nullity of A equal to 2. Okay. So again, now we just substitute the values here in the rank nullity theorem. Now n equal to 5, right? Therefore, 5 equal to nullity of A. We have assumed the nullity of A is 2. So 5 equal to 2 plus rank of A. Okay, from this we can conclude that rank of A is 3. But that is not possible because the rank is at most 2. Okay, so the first option is wrong. Next we go to the fourth option because first option and the fourth options are exactly same. So we see that this option is wrong. Now we go to the fourth option. If you look at the fourth option, we are looking at uh, the elements of r power 5 such that first coordinate and the second coordinate are equal and the remaining three coordinates are equal. Okay, so basically we are looking at first coordinate, second coordinate equal and the remaining coordinates are equal. Okay, and xy varies over r. So they are saying that does there exist a linear transformation R power 5 to R2 whose null space is this space? But what is the dimension of this space? You see, this x is one independent variable and y is one independent variable. Therefore, the dimension of this space is 2. Therefore, if this is the null space of A, we get nullity of A is again 2, but we just saw that their nullity of A cannot be 2. Okay, therefore, again by the option 1, this is not possible. Therefore, fourth option is also wrong. Okay. Next, we come to the second option. They are saying there is a 2 by 5 real matrix such that whose dimension of the null space is 0. What does it mean? They are saying that there is a linear transformation r power 5 to r2 whose nullity is 0. So again we assume there is such matrix. Suppose there is a linear transformation from r power 5 to r2, nullity of A is 0. Okay, but again we substitute it in the rank nullity theorem, we get 5. This 5 equal to nullity 0 plus rank A, we get rank of A equal to 5 from this equation, which is not possible since we know rank is bounded by this dimension of the codomain. Okay, therefore it is a part B question, only one option has to be correct. So option 3 is correct as marked in this problem. So but it is a very nice problem, so we see why option 3 is true. Whenever you prepare, don't just once you know this is the right answer, don't just stop there, you try to prove also. So now they are saying that there exists a 2 by 5 real matrix such that AB is the 2 by 2 identity matrix. So they are saying there exists. So to say there exists, we also construct one example justifying that this option is true. Okay, so now A is a 2 by 5 matrix, B is a 5 by 2 matrix. If you multiply AB, then we get a 2 by 2 identity matrix. So we want one such example that we construct now. Okay, so option 3, they are saying that there exists A from R power 5 to R2, B is, so note that A is a 2 by 5 matrix, therefore it is a linear transformation from R power 5 to R2. and it is given that B is a matrix of order 5 by 2. Therefore, it is a linear transformation from R2 to R power 5 such that we want AB, their product is a identity matrix. Okay. Now you see, uh, so we want AB. So A is a 2 by 5 matrix. A is a 2 by 5 matrix. B is a 5 by 2 matrix. If you multiply, you get a 2 by 2 matrix. That is clear. Therefore, AB is a 2 by 2 matrix. Now, how AB acts? So, if you put a vector V on AB, first you apply B, okay? Then it will, then A will act on, first B will act on V, then A will act on B of V, okay? Therefore, now AB, so first we apply B, okay? Therefore, first B is a map from R2 to R power 5. You see B is a linear transformation from R2 to R power 5. So I have written B is from R2 to R power 5. So once you apply B on, so you take a vector V here and you apply B, you get B of E. B of E, so we say B of E will belongs to the codomain of B. So it is a vector in R power 5. So since it is a vector in R power 5 and E is a linear transformation from R power 5 to R2, A will act on B of E. Okay, so then A is mapped from R power 5 to R2. So when we compose together, we get it is a linear transformation from R2 to R2. We just need one example such that AB equal to identity 2 by 2 identity matrix. So we define the matrix like this. So first I say what is B, then I say what is A. So B is from R2 to R power 5. So I so R2 elements are of the form tuples. So I take x comma y2. The answer should be a 5 tuple. So I take xy2 xy0 0 0. Okay. Now I say what is the matrix A. So now I take a arbitrary 5 tuple, I send it to 2 tuple. So I take the projection onto first 2 coordinate. That is my map A. Okay. Now we find the matrix of the linear transformations B and A. So to find the matrix of the linear transformation B, we take the basis of R2 and find the image and then write the answer as columns. So the basis of R2 is 1, 0 and 0, 1. So image of 1, 0 under the matrix B will be 1, 0 goes to 1, 0, 0, 0, 0. Okay, so we got 1, 0, 0, 0, 0. So image of 0, 1 will be 0, 1, 0, 0, 0. I get 0, 1, 0, 0, 0. So once you have calculated the image of the basis of the domain, you have to put the image as a column. That is one thing you have to remember. Okay, so that is why since we are putting it as a column, that is why this matrix B is it is a 5 by 2 matrix. So even the B is a linear transformation from R2 to R power 5, it is not a 2 by 5 matrix, but it is a 5 by 2 matrix because we are calculating the image of the basis and putting it as a column, not as a row. If you keep it as it is as a row, then you get a 2 by 5 matrix, but we are putting it as a column. That is why the order changes. Okay, 5 by 2. So similarly, now A is a linear transformation from R power 5 to R2. So R power 5 has 5 basis element. So I have taken the image. So what A does, it just projection onto first 2 coordinates, right? So 1, 0, 0, 0 goes to 1, 0. First just 2 coordinates. 0, 1, 0, 0 goes to 0, 1. Just the first 2 coordinates. And 0, 0, 1, 0, 0 goes to 0, 0. First 2 coordinates. 0, 0, 0, 1, 0 goes to again 0, 0 because the first 2 coordinates still 0, 0 only. Similarly for the last element also. So now we have found the image of the basis. Once you find the image of the basis, we have to put it as column. So this 1, 0 is put it as column 1, 0. This 0, 1 put it as column 0, 1. This 0, 0, this 0, this 0, this 0, 0, this 0, 0, 0. So we get yeah, the matrix A. Now you just multiply AB, yeah, sorry, A and B, you will get AB's identity. Okay, so this is one very interesting problem using Rank-Nullity theorem. I hope you understand it clearly. And this is not the only example of AB. You can come up with many varieties of AB. So I urge you to try come up with your own example of A and B satisfying AB equal to 2 by 2 identity matrix. And any doubts, please let me know in the comments. Thank you. Have a good day.